Good morning, everyone. I am Mungra Mahek, and today I'll be presenting my project titled Vending Machine Controller using Finite State Machine with online payment system based on UPI and QR code technology. This project sits at the interaction of two important areas, digital electronic and modern embedded system. The core of this design is a concept called a finite state machine, which is one of the most powerful tool in sequential circuit uh, design. By the end of this presentation, you will clearly understand how a simple vending machine, something we use every day, can be completely modeled, designed, and built using the principle of digital electronic course. Let us begin. So let us start with the basic. What exactly is a vending machine? A vending machine is a fully automated device that dispenses a product, a snack, a beverage, or even a ticket without any human assistance. You insert a payment, make a selection, and the machine does everything else. Now, from a digital electronics point of view, the interesting question is how does the machine know when to dispense and when not to? How does it remember whether you have paid or not? The answer is it is used a sequential circuit. Unlike a simple combinational circuit, when the output depend only on the present input, a sequential circuit has memory. It remembers past events. And this property, the ability to remember a sequence of events, is exactly the that makes the finite state machine the perfect model for a vending machine controller. Real world examples include metro ticket vending machines, snack and cold drink dispenser, ATM ATM machines, airport boarding pass. Basic working cycle is insert payment, verify amount, then it will select product, then dispense it, return change, and reset to idle. Uh, then we go to next. Now, traditional vending machine accept coins, but coins bring problems. Coin jam, fake notes, exact change requirement, and hygiene concern is that this is where online payment specify UPI and QR code become extremely important. With UPI, the user simply opens their phone, scan the QR code on the machine and pays. The bank confirms the transaction within seconds. This confirmation is sent to the machine controller as a digital signal. From the perspective of our digital circuit, this is the most important point. The UPI payment confirmation becomes a single bit digital input. Logic 1 means payment confirmed. Logic 0 means payment not received. The bridge, the gap between the physical world of a online banking and the digital world of a logic circuit. The machine is available 24 by 7. Handles no cache, has no complete transaction record, and is hygienic. Benefits that traditional coins based machine simply cannot match. So let me now formally define the problem we are solving. We need to design a digital controller for a vending machine that accepts UPI and QR code payment. The machine will dispense a product priced at rupees 20, but only after a verified digital payment confirmation signal has been received. The controller is to be modeled as a mode type finite state machine and implemented using D flip-flop and combinational logic gates. Our system has three inputs. P which equal 1 when UPI payment is confirmed, S which is equal 1 when the user select a product, and R which is mutual reset signal. The output are Z1 which is dis dispense signal, Z2 which is idle status LED, and Z3 which is processing status LED. These constraints are important. Only one payment input is accepted at a time. The machine reset after every transaction. and under no condition should the machine dispense without confirmed payment. These requirements guide every design decision we make. So the objective of our project are clearly defined. First, to model the controller as a more type FSM with well-defined state and transactions. Second, to identify all operating states, idle, payment received, selection mode, and dispensing. Third, derive, minimize Boolean expression for next stage logic using the state transaction table and K-maps. Fourth, to implement the circuit using D flip-flop and standard logic gate ICs. Fifth, to integrate online payment confirmation as a digital logic input to the FSM. And sixth, to verify the complete design using a timing diagram and stimulation. Each of these objective corresponding to a specific selection of this presentation, and together they form a complete design methodology. So before we dive into the FSM design, let us quickly review the fundamentals. Digital electronics deals with signal that take only two values. Logic 1, which represent high voltage, typically 5 volt in TTL circuits, and logic 0, which represent low voltage, typically 0 volts or ground. All informations in a digital system is represented using binary number system based 2 using only the digits 0 and 1. A single binary digit is called a bit. 4-bit from a nibble and 8-bit from a byte. The key point here is that every operation in our vending machine controller, every decision, every transaction, every output is ultimately represented as a combination of zeros and ones processed by logic gates and flip-flops. This is the foundation on which our entire design is built. Logic gates are the fundamental building blocks of all digital circuits. They take binary inputs and produce binary outputs based on a specific Boolean function. The AND gate produces a logic 1 output only when all inputs are 1. In our project, we use AND gates to check whether both payment P and selection S are simultaneously valid before triggering a state transaction. The OR gate produces logic 1 when at least one input is 1. This is used to combine multiple triggering conditions in the next state logic. The NOT gate simply inverts the input. It turns 1 into 0 and 0 into 1. We use this to generate a complemented state variable needed in Boolean equation. NAND and NOR gates are called universal gate because any Boolean function can be realized using them alone. The XOR gate output 1 only when both inputs are different, used in error detection and party logic. You can see from the table on the screen that each gate has a specific application in this project. Understanding this gate is essential because the entire next stage logic of our uh, FSM is built from them. So it's important. So now there's a difference between sequential versus combinational circuit. So first is a combinational circuit. So combinational circuit is one whose output depend only on the present input. Uh, it has no memory. Give it the same input and you always get the same output. Example include adder, multiplexer, and encoder. A combinational circuit is not suitable for our vending machine because it cannot remember whether the user has paid or not. A sequential circuit, on the other hand, has memory. Its output depend on both the present input and the current state, which captured the history of past inputs. The circuit remember what happened before the current moment. This is exactly what we need. Our vending machine must remember that payment has been received even when the payment signal P goes back to zero. It must hold that information until the product is dispensed. This is why we use flip-flops to store state information, and this is why our controller is a sequential circuit specifically modeled as a finite state machine. You can see both types compare side by side on screen. The sequential circuit column highlighted with a gold checkmate. This is what we in this project. Since our controller is a sequential circuit, we need a memory element. That memory element is a flip-flop. Flip-flop is a bistable circuit, meaning it has two stable states, Q equals 0 and Q equal 1. It can store exactly one bit of data. A key property is that its state only change on the active edge of the clock signal, either the rising edge or the falling edge. This makes the flip-flop synchronous, which is essential for predictable glitch-free operation. In this project, we specifically use the D flip-flop, also called the data flip-flop. Its behavior is beautifully simple. On every rising clock edge, the output Q takes the value of input D. So Q at time t plus 1 equal D at time t. That's it. Because our FSM has four states, we need to encode those states using binary. Four states require log base 2 or 4, which equals 2 bits. So we need exactly 2D flip-flop. Let us call them FF1 and FFO, producing state bits Q1, Q0. The two flip-flops together from the state register the memory of our FSM. You can see that this uh, truth table where d equal to 0 gives q is equal to 0 and d is equal to 1 gives q is equal to 1. So the equation q t plus 1 is equal to d. And here are some types of flip-flops like SR flip-flop, which is set reset, JK flip-flop, which is universal no valid state, day flip-flop, which is used in this project. We are using as it's simple, and T flip-flop used in counter. So let us look on finite state machine. At any given moment, it exists in exactly one of a finite number of predefined state. When it receives an input, it may change from its current state to a new state. This change is called a transition. The machine also produces an output which depends on its state. Mathematically on FSM is defined on a phi table, which is this M is equal to Q uh, sigma, delta, Q naught, and F. And here Q is a finite set of all state. For our machine, Q is equal to S0, S1, S2, and S3. Sigma is the input alphabet, the set of all possible input. Here is a signal P, S, and R. Delta is a transition function. It takes the current state and input and tells the next state. Q naught is the initial state. F is the set of final or accepting state. For us, S3 the dispense state. The reason on FSM is so well suited for vending machine is that machine has a limited, clearly defined set of condition, clearly defined inputs and clearly defined responses. It is deterministic, no ambiguity. Types of FSM there are two: More and mailing machine. In a More machine, the output depend only on the current state. Output are written inside the state circle in the state diagram. The output is synchronous with the clock. It change only when the state change. In mailing machine, the output depend on both the current state and the current input. output are written on the transaction arrow. The output can potentially change asynchronously. The moment an input changes, the output can change even without a clock edge. Look at the comparison table on the screen. You can see that the Moore machine requires more states than the Melee machine for the same problem, but its output are stable and glitch-free. Melee machines required fewer states but can produce unwanted output glitches when input changes momentarily. For our vending machine controller, we have chosen the Moore machines. We have chosen the Moore machine, and we will justify why we choose Moore machine in next slide. In this, we are using this. So let me now justify why the Moore machine is the right choice for our vending machine controller. The most critical reason is safety and stability. In the vending machine, a false dispense signal, even for a fraction of a second, means the machine gives away a product for free. This must never happen. The Moore machine produces output that is synchronous with the clock and stable between clock edges. There are no glitches, no false trigger. The second reason is simplicity. In a Moore machine, the output depends only on the current state, not on the input. This means the output logic is simple to derive and simple to implement with fewer gates and simpler to debug even. Third from a is it it is equals predictable, safe, and simple. These three properties make it ideal choice for the real world controller. So let us now look at the system overview of our vending machine. The big picture before we go into the detailed logic design. The system consists of 5 main blocks connected in a pipeline as shown in the block diagram. The first block in the UPI or QR payment system. This is our user-facing interface. The user scans the QR code and initiate the payments from their mobile device. The second block is payment interface module. This is a hardware, typically a microcontroller with Wi-Fi module like ESP32 that calls the bank API, receives the payment confirmation and convert it into a digital logic signal P equal to 1. The third is FSM controlling or more machine implemented with D flip-flop and combinational logic gates. This is the brain of the system. The fourth block is actuator driver, an IC like ULN 2003 or L298 and that amplifies the weak logic signal into enough current to drive a motor or solenoid. And the fifth block is dispense mechanism, that physical component that releases the product when activated. Notice. Let me now define every signal in the system precisely. We have four inputs. P equal 1 means UPI payment has been verified by the bank. S equal 1 means the user has pressed the product selection button. R equal 1 in a manual reset signal that return the machine to the idle state from any state. And CLK is the clock pulse. Its rising edge triggers the state transition in our D flip-flop. We have three outputs. Z1 is the dispense signal. Uh, when Z1 equals 1, the motor activates and the product is released. Z2 is the idle LED. Green light indicates the machine is ready and waiting. Z3 is the processing LED. Yellow light indicates the machine has received payment and is awaiting selection. Now the most important question is in this project is how does a UPI payment become a digital input? Here is the answer. The user scans the QR code and the UPI app sends the payment to the merchant account. The bank confirms the transaction via its API. Our microcontroller connected to the internet via Wi-Fi. receives this confirmation and immediately sets the signal P to logic 1. The logic 1 pulse is the trigger that starts the FSM transition from idle to the payment receive state. This is a bridge between the digital world of logic circuits and the real world of online banking. So near how UPI generates a digital signal is this a five-step process. What is FSM design? Defining the state as 0, encode as Q1, Q0 equals 0. 0 is the ideal state. This is the initial state of the machine. No payment has been received. The green ideal LED output Z2 is on. The machine is waiting. This is also called the reset state because whenever R equal 1, the machine returns here. State 1 encode as a 0, 1 is the payment receipt state. The machine has received and confirmed the UPI payment P, and P was 1 in the previous clock cycle. The yellow processing LED Z3 is now on. The machine is ready and waiting for the user to press the selection button. States S2 encoded as 1, 0. The selection made state. Both payment and selection have been confirmed. The machine internally prepared to dispense it and verify all conditions. And the last one is S3 encoded as 1, 1. Is dispensing state. This is the state where the machine actually acts. Output Z1 equal 1. The motor or solenoid is activated and the product is released. This state lasts for exactly one clock cycle, after which the machine automatically reset to S0. Notice that we need exactly 2 bits to encode 4 state, and that is why we need exactly 2D flip-flops. And the cycles continues. This is a state transition diagram, the graphical heart of the FSM design. Every state machine design starts here. Each circle represents a state where you can see S0 at the left. Here it is. And S1 and S2 are here at top, and S3 is here is shown in gold at the bottom, indicating it is an active output state where Z1 equals to 1. The arrows represent transition. Let me walk you through the complete operation. The machine starts in S1, then ideal. If P equals 1, then that is UPI payment is confirmed. On the next clock edge, the machine transition to S1, that is it will go here. And if in S1, if the user now presses the selection button S equal 1, the machine moves to S2. And in S2, all conditions are verified. The machine transition goes to S3, the dispense state. From S3, the machine automatically returned to S0 after one clock cycle. It looks like a cycle. This is shown by the dashed gold arrow labeled auto reset. This is also a self loop on S0 when P equals 0. The machine stays in idle. Most importantly, look at the note here. If R equals to 1 from any state S0, S1 or S3, the machine immediately jumps back to S0. This is asynchronous reset with the highest priority in the system. This diagram is a reference for deriving everything that follows. The state transition table Boolean equation in this circuit. So we are on a state transition table is the algebraic form of the state diagram. It captures every possible combination of present state and input and tell us the next state and the output. Let me walk you through the key rows. First row present state is S0, Q1, Q0 equals 0. 0. Inputs P, S, R are all 0. No action. Next state is S0. Ideal LED Z2 equal to 1. Then row to present state S0, P equal 1, S and R are 0. Payment received. Next state is S1, Q1 star, Q0 becomes 0, 1. Processing LED Z3 turns on. Row 3, S0 with R equal 1 reset from ideal machine stays in S0. Ideal LED remains on. In row 5, S1 with S equal to 1 selection made. And machine moves from S2 to Q star Q0 star equal to 1 0. Then in row 7, S2 with both P equal 1 and S equal to 1. P and S equal to 1. Full verification machine moves to S3. Dispense signal Z1 becomes 1. Row 9 Z3 is the dispense state regardless of input, all marked as X, meaning don't care. The machine automatically returns to S0. In the next clock, ideal LED Z2 turns on back on. So we are looking forward for working principle. Step 1 is power on or reset. The FSM enter states is S0 ideal. The flip-flop output Q1 equals 0, Q0 equals 0, and the green ideal LED turns on. Step 2, the user sees the machine is available and opens their UPI app. Step 3, the user scans the QR code on the machine and initiate a payment of rupees 20. Step 4, the bank confirms the transaction. The payment module receives the API confirmation and sets P equal to Q. P equals to 1. Step 5. FSM transition from S0 to S1 on the next rising clock edge with P equal to 1. The D flip-flop updates Q1 stays 0, Q0 becomes 1. We are now in the state S1. The yellow processing LED turns on. The step 6. The user presses the product selection button. S equals 1 in generate. Step 7. FSM transition from S1 to S2 on the next clock edge with S equal to 1. Q1 becomes 1. Q0 becomes 0. We are in S2. Now step 8. FSM transition from S2 to S3. The combinational circuit verifies both payment and selection on the next clock edge. Q1 and Q0 both become 1. We are in S3. The dispense output Z1 goes high. Z1 equals 1. Activate the motor driver. The motor rotates. The solenoid opens. The product falls into the collection tray. On the very next clock cycle, the FSM automatically reset to S0 and is ready for the next user. So what are the hardware components used? Are microcontroller like ESP32 or Arduino. It is preferred because it has built-in Wi-Fi, allowing it to communicate with UPI payment API directly. It runs FSM logics and derives all output. The D flip-flop IC we use, which is dual D flip-flop in a single chip. Two flip-flop are available, which is exactly what we need in Q1 and Q0. The logic gate ICs, the QR code display, uh, the DC motor, solenoid valves, because it activates by Z1 equals 1 to physically release the product. Motor driver ICs, then we use LED indicators, red, green, yellow for status output. Then we use 5-volt power supplies, SMPS or battery. uh, it's used for power source, used as a power source. This slide connects the theoretical digital electronic concept we studied to their practical role in building the actual machine. Every decision the machine makes, dispense or wait, accept payment or reject. It is a binary logic operation at its core, and end of payment selection and or of possible condition. A not for complement logic. A flip flop are just not just component, they are machine memories. Without them, the machine would forget that a payment was made the moment payment signal returns to zero. The clock synchronously everything. Without the clock, multiple flip-flop might update at slightly different time, creating what are called rest condition, inconsistent, unpredictable states. The clock prevent this entire. The K-map minimize Boolean equations are directly implemented as IC chips on the PCB. Every AND gate on the 74LS08, every OR gate on the 74LS32, each one implement a specific term from a logic equation. And finally, the UPI payment integration shows the digital electronic is not isolated. It interfaces with the internet, with banking APIs, with user apps to create a complete real-world embedded system. So advantage of online payment vending machine is no cash handling, 24/7 availability, instant and accurate, hygiene operation, easy maintenance, transaction logging, scalable design and secure, and even traceable. Even it has some limitation, and it's important to acknowledge them honestly. The most critical limitation is internet dependency. UPI payment require an active internet connection. If the network is down, the machine cannot accept any payment and become completely non-functionable. Second, latency. Bank API response typically takes 2 to 10 seconds. During this period, the FSM must wait, which require a timeout handling mechanism not present in the basic design. Third, no refund mechanism. And then fourth is single product limitation. The current model handle one fixed price product. A multi-product machine required a significantly expand FSM with more states. Fifth is power failure vulnerability. If power is low while the machine is in state of S1 or S0 after payment but before dispensing, the user loses money without receiving a product. Non-volatile state storage would be needed to handle this. The future scope and enhancements are multi-product support, which is already implemented, FPGA implementation, IoT and remote monitoring, then biometric verification, online payment mode, automatic refund state, AI-based demand forecast, and solar-powered operation are future scopes. This enhancement shows that this project is not just an academic exercise, it is a foundation for commercially visible products. To conclude, in this project, we successfully designed a complete vending machine controller using a finite state machine, especially the more model integrated with UPI and QR code base and in digital clock, D flip-flop logic gates like AND or NOT and K-maps, minimization from hardware, backbone, etc. And thank you for your attention and goodbye.